Okay, so before we get started, just a reminder that the homework 4 is due Wednesday. So I realized that the homework problem, like for example, the number 2, which regarding the one of the 3-point geometry, it might be tricky. So I'm going to talk about it right after I finish the SSS scheme. So first of all, oh, actually, I need to ping my video, otherwise other people will be in there. Okay, so first of all, my plan for today is the following. So remember last time that I want to show the proof for SSS, but I didn't manage to do it. So at least for the case 1. So I'm going to finish up and then I will give you the hint for case 2 and case 3. Okay, so I believe if you already done it or if you already read through the case 1, it should be more or less pretty straightforward, but I can give you some hint in case you need it. And after this, I will talk a little bit about the problem 2 in homework 4, just to clarify and also give you some hint. And if time permit, I will want to talk about one of the question I grade for the homework 3 you turn in. And then we will continue to the section 7.1. So let's see, so let me turn this. So first of all, I need to recall essentially the axiom 3.5. So I actually copied down a lot of things from last time. So first of all, Hilbert's axiom 3.5 basically says this is like an almost SAS, right? So it says if you have 2 triangles satisfy essentially the condition, the assumption for SAS, then last time we talked about that it's almost SAS, but the conclusion only tells you that you will only have 1 angle or essentially 2 angles which are equal. And this is the axiom we're going to use in a minute. And axiom 3.4 also tells you that you can reproduce an angle, right, on either side of the line. Okay, so I just want to briefly mention it because we're going to use it in a minute. So actually, last time we kind of start the proposition 1.8, the SSS. So essentially, this tells you, let me remind you, right? So we know SSS by now that if AB equals DE and AC equals DF and BC equals EF, I want to prove that these 2 triangles are congruent. And congruent means that every corresponding sides and angle are all equal. So last time we mentioned that first, in this order, first by 3.4, the one that we can reproduce the angle, we know that you can find a unique ray, AC prime. So essentially we draw like an AC prime here, such that the C prime AB, this angle, is going to be the same as FDE. Okay, so I can definitely copy or reproduce an angle like this, right? And then on the side of AB, essentially we can like only find one such ray, AC prime. And so this is done or justified by 3.4. Then at the same time, by 3.1, it tells you that we can reproduce a segment. So that essentially gives us the justification for choosing or constructing AC prime such that AC prime is the same as DF, right? So DF is the double bar here, so let me put double bar. And we know that DF essentially, by the assumption we have, it's equal to AC. Okay, so that's the information we have. And we know that C prime, we choose C prime to be on the opposite side of AB as C. So C is on one side of AB and C prime is on the other side. So now we can join BC prime by essentially one of the axiom. Okay, so now we're going to compare these 2 triangles here. Okay, so now let's see what information we have, right? So let's say, so AB equals DE, right? So AB, we have AB here, and we actually have a side AB here, right? And equals DE, so I put 1 bar. AC prime is DF, right? That's double bar, like for another side. And you can see that C prime AB is the same as FDE, right? So if you compare DEF and the other new triangle AC prime and B, then we know that essentially we have the SAS scheme. So we can conclude that at least for now, the triangle DEF is congruent to ABC prime. Okay, so now you might wonder, okay, my goal is to conclude DEF is congruent to ABC, but we are kind of using ABC prime as an intermediate tool, right? So first we conclude that these two are congruent, then we can first get the conclusion that BC prime is going to be the same as EF, which means that actually this is a bad picture because it's not represented very well, the picture. But so that's why I need to use the bar to keep in mind myself, like which side is equal to the other side. So we know BC prime is going to be the same as BC and also as EF, right? This is all same. So first equality, this is essentially proof because the DF and ABC prime is congruent. But by assumption, this is given that EF is equal to BC. Okay, so now we have all this information, and also we have BC equals BC prime. So let's put this. Okay, so now let's see. So you can see from this picture that essentially C prime is on the other side of AB. So you can imagine that's like if you extend this middle edge, like AB, this middle line long enough, then C and C prime, if you connect it, it's going to intersect the line AB at some point, okay? So if you already work on this problem, then you definitely know what I'm talking about, or like already knew what's going on, but let's just do a review. So let's connect C and C prime, right? And C and C prime is going to intersect AB at a point G, right? So you can see that there are going to be three cases because the way I draw the picture is very kind of a special case, very specific. So it turns out that there will be three cases that we are going to see. So, okay, up to here, we're going to, depends on where the point G is, or you can say where the relative position of G and AB is. There's three cases. And what's the goal here, right? Remember, we just proved that the triangle DEF is congruent to ABC prime. So the next thing we want to do is we want to prove, like, I mean, case by case, right? For those three cases, we want to prove triangle ABC is going to be congruent to ABC prime, right? Then now, essentially, both DEF and ABC are congruent to the same triangle. Then we can conclude that ABC is indeed congruent to triangle DEF. Okay, so we essentially use the intermediate ABC prime. Okay, so some of the problem probably you're going to see is going to be like this. Sometimes you need to create an intermediate tool. Okay, so the case one, which is definitely included in the textbook, is essentially, I would say, the model case, right? So first of all, you can see that the first case I want to consider is when the point G lies in between A and B, right? So please be careful when you draw picture, unless you have like a very firm evidence, do not assume what you saw is, I don't know, like sometimes the picture can be misleading. For example, for now, it looks like that, like for example, like AB is perpendicular to CC prime, but we don't have any evidence yet to justify it or to conclude it, right? So you can see that my picture here, even though the segment C and C prime looks like intersecting AB perpendicularly, but I have no evidence to support that yet. So I cannot just say that, oh, it's perpendicular, okay? So do not make this kind of mistake on homework or exam later on, unless you are sure that you have a firm evidence for supporting a certain statement. Otherwise, you should not just because the picture looks like it and you conclude it. And that's one of the reasons that I insist everyone, when you prove the especially the homework for now, you need to justify, right? From one step to next step, right? If you want to write down that something is true, you should say that it's by whatever proposition or axiom or postulate, right? If you have this good habit, then you essentially train your mind to ask yourself, do I really know this is true? Or I make it up, or I got fooled by the picture, right? So once you have the good habit, develop the habit of justify each step, that will also train you or test you whether you can convince yourself that the statement you make is correct. Okay, so that's one thing I want to address. So first of all, let's see, there are three cases. One is G is going to lie in between A and B. Okay, I'll come back to proof, but I want to show you what three cases we have. Second case is that it's possible that depends on your triangle, right? A, B, and C, or A, B, and C prime. It's possible that G can be, happens to be the same point as A or B. And in either case, it's going to be similar. So so you can just prove one of the case when G equals B, that's fine. And the third case is when G is actually outside of A and B. Essentially, G lies outside of the segment A and B, which means you can pick one of the point, put it inside. So we consider the case that B is lying between A and G. So you will have these three cases, but I guarantee that the proof is more or less the same. Okay, so let's see the case one here. So first of all, let's write down all the information we have, right? So we already know that AC is the same as AC prime, okay? And BC prime is equal to BC, right? So let's see why this is the case, right? So we already know that AC prime equals AC. This is by the construction we choose, okay? BC prime equals BC. This is essentially by what we prove, like before the case one, that DEF is equal to ABC prime, and use the other assumption. So we have these two, okay? So now we consider, so let me make a mark here. So AC is what? AC is double bar. AC prime is the same as AC. And BC is triple, which is, okay. So I have all the information here. Then let's consider, so now you can see we have exactly two isosceles triangle. So consider two isosceles triangle. So one is CAC prime, and the other is CBC prime, right? I mean, from the picture, we know that. Okay, so now by one of the proposition, I want to be more specific, 1.5, we know that the base angle of isosceles triangle will be equal, okay? So we know that we have two pair of angle. ACC prime is going to be the same as AC prime C, right? So ACC prime. So this angle is the same as this one, okay? And for the other isosceles, we have also the same thing. So BCC prime is going to be the same as BC prime C. So let me use different color here. Okay, so now you can see that we actually have like a bigger angle, right? If you consider the angle ACB, the sum of those two, the blue and green one, right? Then you can see we have a bigger triangle, bigger angle here. So we can consider the angle ACB, which is essentially the sum of the two angles that I just mentioned. But you can see that this is going to be the same as the other one, which is essentially the same as angle AC prime B, right? So in other words, you have this bigger angle, which are equal, right? So now we have all the condition we have, right? So you can see that we have this AC equals AC prime, BC prime equals BC, and we also have this angle in between, which are equal, right? Then this is essentially obviously SAS. So by SAS scheme, we know triangle ABC is congruent to triangle ABC prime. But back then we already proved that ABC prime is equal to congruent to DEF. So essentially you can conclude for this case, the triangle ABC and DEF will be congruent. Okay, so you can see that it's not that bad at all. Like you just need to put up all the information you have here. Okay, so let's see. So one thing I also want to emphasize, this is also my thought from grading the homework. One thing I want to remind everyone is that when you mention the congruent scheme, please directly mention. I mean, I know some people will say a proposition which and which, but to be more precise, it's better you mention explicitly which scheme, right? For example, SAS or SAS. Because, for example, one of the proposition, I think it's 1.26, it contains two schemes, right? So if you only tell me 1.26, then I don't know whether you are talking about ASA or AAS, something like that. So please be more specific so I know that you understand which scheme you are using, okay? Especially that you may like miscited, right? Like you might miscited the proposition. So for congruent scheme, please just directly tell me which scheme you are using. That's more straightforward. Okay, so as I said, because the homework is for case 2 and case 3, but you can see this is not too bad. So especially for case 2, I can just write down or draw the essentially the information, right? So remember that actually we already know AC is equal to AC prime, and BC is going to be BC prime, right? And so you need to see that how am I going to make these two triangle the same, congruent, right? And you can see that it shares the common side. Okay, so I'm just going to stop here. The answer is just pretty much in the picture. Okay, so your goal still want to try to prove ABC is congruent to ABC prime. Okay, so from this picture, you already have all the information you need. So case 2, I would say, in some sense, even much more easier than other cases. Case 3, you need to do something similar to case 1. So now you can see that now we should also have two isosceles triangles. So let me draw the essentially the information we have, right? So AC prime again will be equal to AC, right? This is already known before even we start the cases. And we also have BC equal to BC prime, right? So now the thing is that, okay, you can see that we have one bigger isosceles triangle, right? Which is the larger one, ACC prime. So you can see that, of course you need to write down the detail, but I'm just going to say it to give you some hint. So you can have this, you will have this base angle which are equal, right? Because that's the one of the bigger isosceles triangle. But at the same time, you also have smaller isosceles triangle, right? The BCC prime, which means this smaller angle here should also be equal, right? If that's the case, after you take the larger angle, subtract the smaller one, you should also get the same, you should also get the same smaller angle here. The red one will be the same, right? Now you have two sides smaller angle, then you should be able to still prove that ABC is congruent to ABC prime. So it shouldn't be too bad. So technically case 1 is addition. Case 2, you should somehow use subtraction. Okay, I'm pretty much tells you what to do here. Okay. Okay, so this is for homework, but with this picture, it should give you pretty much all the information. So another thing, as I promised, I want to talk about the homework, the number 2 from the 3-point geometry. Give me a second, I want to point out the axiom. So, okay, so so let me see, this is number 3 in section, I believe 6.2. Okay, so this is 3-point geometry. Okay, so one thing I want to clarify is one of the statement here. So the axiom 3, right? So it says 2 distinct lines are on at least 1 point. Okay, so 2 distinct lines are on at least 1 point. So to clarify, what does that mean in terms of picture, right? So it essentially means that 2, you can think of on, in this case, is meet, right? Or intersect. Okay, so it means if you have any 2 lines, right, it can only intersect or meet each other at 1 point, right? So you might have this kind of picture, or maybe, it depends on how you're going to draw it, okay? Where your point is, essentially. So also keep in mind, this is something I mentioned before, but I want to emphasize that when we talk about finite point geometry, right, either 3-point or 4-point, this is very different than the Euclidean geometry we saw before, right? Because you only have finite many points, right? I mean, this one, you only have 3 points, right? The example we did in the class is 4 points. So it tells you that the concept of line here is very different than the usual sense of line, right? The usual sense of line that we all know of is like infinite many long, contain infinite many points, right? But here you should think of the line here, we should interpret as one way you can do it, I saw like elsewhere, like people give me a good idea of this, is that think about the line here in this geometry as some kind of committee, okay? And the point here means a person, right? So you can have a person in the committee, right? In other words, your committee may have 1 person, 2 people, 3 people, or no people, right? So this means that it depends on where you want to put the point is, right? For example, you might be able to have a line and then there's only maybe 3 points on it. Or you can have a line which have 1 point or no points. Okay, depends on your need, okay? So essentially you can say that, for example, I can say that essentially these 2 lines I draw here does not intersect at any point, sorry, right? Because it doesn't intersect at the point I put there, okay? But the second picture I just drew now do intersect at 1 point, okay? So let me put it here, intersect at 1 point. The 2 lines don't intersect. So be careful, don't be fooled by the picture. Think of lines as some kind of committee, okay? Right, so you can say that, oh, I put 2 committee there, but there's only 3 people in one of the committee. The other one is, I mean, doesn't have anyone, so it doesn't intersect or like overlap, right? And another thing I want to give you a hint is that, for example, that, okay, so I think this is part C. So part C says you want to prove that the exon 1 is independent, which means, in other words, you want to draw a picture while exon 1 is violated, but the other, the other 3 are true, right? So to violate exon 1, what's exon 1 here? It means it says there exists exactly 3 points, right? So let me give you a hint that in this case, you probably need to draw a picture or a model which has more than 3 points, right? So you might be affected by the example used in the textbook where they draw only 2 or something, like 2 points, something like that, but it may not work here for 2 points. So you might want to draw a picture with more than 3 points, maybe 4, okay? So that's allowed, right? As long as the first axiom is not satisfied, it doesn't matter how many points you draw, as long as the other 3 axioms are satisfied. Okay, so these are the hints that I think hopefully will be helpful because I want to make this clarification. I think this is the question I kind of got over the weekend. Okay, is there any questions so far for this one, right? Since I'm on this, so I think I could just directly talk about it.
I have a question.
Yeah, sure.
So for 3E, can we construct a line such that 2 lines are parallel to each other so they never intersect?
So you don't need parallel. So the concept of parallel don't exist here. As I said, like for example, like this picture, right? I'm circling here, right? I can say these 2 lines do not intersect each other because the line here, as I said, it's not the usual sense of line we thought. You can think of the line here as a committee, right? So the line 1 is like a committee with no people in it. Line 2 is a committee with 3 people, right? And you can see that those 3 points does not on L1, right? It's not in the committee 1. So essentially they don't intersect. They don't, like, for example, this intersection is fake, right? Because we don't have infinite many points on the line. It's not the usual sense of line here because we only have finite points, right? Like keep in mind, this is a finite point geometry. You will see that this kind of phenomena also occur in the 4-point geometry, right? We're trying to draw a model where the two lines seems to cross each other, but the points we put doesn't really lies on there. So those two lines actually don't intersect. So this means that you don't need a concept of parallel. In this geometry, we don't have, we didn't have any, is that, I heard some background. Okay, so so essentially that you need to be careful, right? Like you don't really, like in order to introduce the parallel concept, you need to include it in the axiom, right? Remember, we actually include this as one of the postulate or actually definition, right? So you don't have it here. And I would say you don't need it, right? So like the picture I just circled here, even you have two lines, seems to intersect, but they don't really intersect. So I would say you don't need it, okay? I think I know what you mean, but if you're not sure whether your picture is correct or not, send me an email. But you don't need the concept of parallel here. Yeah.
I got it. Yeah. It's good.
Yeah.
Yeah.
Okay. Any other questions? So you might want to think about this problem is like a puzzle. I think to me it's quite interesting. Like I trying to find, like draw a picture where other conditions satisfy. It's like a game. Like it's not that hard. Like I would say probably you don't need to do like a very complicated picture. And I would say the example they used in the textbook, the 4-point geometry, will also be a good reference as well. Okay. Okay, so I want to also briefly talk about homework 3 that I graded because this is very simple. I can just use 2 minutes. And so this is, oops, not section. Number 1 in homework 3. I think this is problem 5 in section, this is 3.3, okay? So most people are fine with this problem. So it tells you that you have a triangle, a isosceles triangle with AB equals AC. This is given. And they also tell you you have a picture like this, some points D and E here. Okay, my picture is very bad, but just, this is 1, this is 2. And they also know that angle 1 equals angle 2. And that's the only information we have. And they want to prove, they want you to prove that ADE is isosceles. Okay, before I tell you the correct answer, I want everyone to think about or recall, just tell yourself, right? What's the definition for isosceles triangle? Okay, you should have an answer for yourself, okay? Then, before I prove this, I want to remind you the definition for isosceles triangle is simply a triangle with 2 equal sides, and that's it, okay? So the reason I want to mention this first is that I found that several of you trying to prove extra, right? Not only you like once you get the point, once you get to the point where you prove AD equals AE, then that's done, right? Because you already proved that this triangle has a pair of equal sides. And some people want to do more by proving base angle to be equal. It's not necessary, okay? But at the same time, I also see people, instead of proving 2 equal sides, they prove to me 2 equal angles, base angle. That's not quite right yet, because by definition, the isosceles triangle means a triangle with a pair of equal sides. So if for some reason, instead of directly proving AD equals AE, you prove base angle to be equal, then you need to use, I think, proposition 1.6 to tell me that, oh, then it's AD equals AE, but that would be a detour, okay? So first, the definition, you need to be careful, okay? Second, how to prove this. This is, if you know what to do, it's actually, I would say, 2 lines, okay? So first of all, you already know AD equals AC. So essentially, by proposition 1.5, you know angle B is the same as angle C. Okay. now you can see that you have this angle B equals C, and we have AB equals AC and angle 1 equals angle 2. So this is exactly ASA scheme. Then right away we have triangle ABD is congruent to ACE. So we can prove directly that AD equals AE. And once you reach this part, you're pretty much done. Because by definition, you have a triangle with 2 equal sides. So you can tell me ADE is isosceles, and that's it, right? So this is supposed to be an easy problem, but I see a lot of redundant part or detour. And also do not assume that you know the position of D and E. I've seen like some people tell me that D and E is, I don't know, like in certain position. You don't have, it's not true, okay? And also I've seen some people trying to draw like a perpendicular line here or something like that, but you need to be careful, right? Like if you pick out the midpoint, you need to justify. I think this is one of the theorem 3.5 we proved before, that like you need to justify why when you connect A and M, it's happened to be perpendicular, right? So if you do this kind of like extra or detour method, you want to be careful, but actually you don't need it. I would say you don't need it. So let me just take it out, right? You don't actually need it. The only information you need is on the picture here. So be careful. I also, oh, actually there's a common mistake. I do see a couple students do that, is to claim that BD is the same as CE just because angle 1 is equal to angle 2. So this is not true, okay? You cannot just because the picture looks like it and you say it's true, okay? So that's why I want to emphasize that if you want to say BD equals CE, you need to show me the evidence. You cannot just say because the picture looks like it, right? And it's not going to be true just because angle 1 is equal to angle 2, right? For example, I can give you a counter example, right? You can have something like this, right? An angle A, right? And then let me draw maybe a little bit more exaggerated. You can have 2 triangles like this, but angle A is the same as angle D. Can you say now that BC is equal to EF just because they're opposite to the same angle? No, right? So be careful. You should not claim something that you're not sure it's true. That's why I keep emphasizing that whenever you say something is true, you should always give me the reason. Even when you claim 2 triangle is congruent, you need to tell me the reason. You cannot just say, oh, these 2 things are equal, and then without giving me the evidence. If that's the case, I will have to take out quite a lot of points, especially in the exam, because that means you don't know how to justify the things you just claim. Okay, so that's essentially all the remark that I want to make regarding the homework and also in general. Okay, so I'm going to go start the 7.1. So basically starting from chapter 7, it's going to be quite spatial in the sense that this is what we call the non-neutral geometry. So let me remind you what's neutral geometry. Neutral geometry is essentially what we have done in chapter 3 and also chapter 6, for example. So neutral geometry means that all the proposition or result or theorem we have obtained does not depend on the 5th postulate or the so-called parallel postulate. So it only depends on the first 4 postulate, okay, and other common notion. Just take out the 5th, right? So, but it turns out that there's also what we call non-neutral geometry, means starting from chapter 7, especially in chapter 7, the results we are going to see it's going to depend on 5th postulate, okay? Which means we're going to talk about quite many results that will be related to parallel lines, okay? So before we can talk about parallel lines, let me remind you the definition of parallel lines, okay? So parallel lines, or you can say parallel straight lines, are straight lines which if you, I mean, here we want to emphasize they're on the same plane, right? Because if they're in the space, then you will have like 3 different cases. So we restrict ourselves, everything is on the same plane. And if you produce or extend the line indefinitely in both directions, then if it's parallel, that means the definition is that they do not meet each other in either direction, which means that in sometimes if you want to prove to me or claim that two lines are parallel, you cannot just say that, oh, they don't meet at one side. You should essentially tell me they don't meet at either side, both sides, right? So the first theorem, actually this section 7.1 only include one large theorem, okay? And it actually takes some time to prove it. So actually it turns out my original plan for this session 7.1 is to, like last year what I did in class in person was that I want people to separate into groups and do like some kind of group discussion and ask someone to come on board. And I was planning to do that, but in the last minute, I realized that not everyone have a proper, say, like a touch screen, or it's very hard for people to like write on the thing and show it to everyone on Zoom without having proper equipment. So I kind of abandoned this idea. So I'm going to do it myself, but so then this will take a little bit longer probably. So theorem 7.1, the only theorem in this section, is very important because it essentially gives you several equivalent statements of the fifth postulate. Okay, so essentially 7.1 tells you if you assume the first four postulate, right, assume neutral geometry means postulate 1 to 4, then we can prove the following 5 statements, one of them is actually the fifth postulate, are all equivalent, meaning we actually found 4 other alternative or substitute for fifth postulate. Okay, so that's why this is very important. So I'm going to go over the 5 statements, that the 5 equivalent one, and I'm going to prove one by one how to show that these 5 are all equivalent. And I can tell you most of, like pretty much, I think 4 out of the 5 proof we are doing here are essentially based on proof by contradiction. So it's going to be a very nice practice for you, all of you, to understand the proof. And they're all written, I think they're all written in the modern language. So it's, I would say it's, but you need, it doesn't mean that the proof is easy. It just means that it's probably it's quite straightforward to understand. But you still need to sit down and then think about it, because the logic, you need to kind of think it through. So let's do it one by one. I want to go over the statement, and then we're going to see how to prove that these 5 statements are equivalent, okay? So first statement is essentially the fifth postulate. So it says, let me remind you, it says if you have a straight line falling upon to another straight line, okay, like what I drew here, making the interior angle on the same side the sum less than 2 right angle, right? So you have M crossing L1, L2, making the sum of the interior angle, right, on the same side, 1 and 2, to be less than, oh, actually, I want less than, sorry, this is less than. If it's less than 180, right, then it tells you if you extend these 2 lines indefinitely, right, they're going to intersect or meet on the same side as those 2 angles. So you can see that if you extend L1 and L2 indefinitely, then at some point it's going to intersect each other. So if you want to draw a picture to remember what this fifth postulate talking about, then it essentially say if this interior angle, the sum is less than 180, then L1 and L2 is going to meet, or you can say will meet at a point on the same side as this 2 angle. Okay, so that's essentially the fifth postulate. So it turns out you're going to see that most of time, or sometimes, that people don't like this fifth postulate. They like to use the other equivalent statement, and usually what we call the playfairs, because playfairs are easier to use in some sense. And so we're going to see this statement in a minute. So second statement, which is going to be proof that it's equivalent to the first one, is this, what we call the proposition 1.29. So it says if you have a parallel, if a straight line falling on 2 parallel lines, okay, then it's going to have three conclusion, right? So that you can see the picture here. If L1 is parallel to L2, then we have three things. First thing, the interior, maybe I should be more precise. The interior alternate angles is going to equal to one another, right? So the first part, A, is that we're going to have that the interior alternate angles, that's essentially 1 and 2, is going to equal to one another, okay, right? Because let me circle out this two angle, 1 and 2, is going to be the interior alternate angles. It's going to be equal to each other. Remember, we've seen something similar, but converse of it. I think that was maybe 1.27, right? We said that if 1 equals 2, the angle 1 equals 2, then the lines are parallel, right? Back then, we only have converse. This time, we do the other way around, right? So that's the first conclusion. And second, again, if two lines are parallels, then the exterior angle will equal to the interior opposite angle. In just one notation, this essentially tells you angle 2 is equal to angle 3. Okay, you probably already seen this in high school. This is something we definitely see before. And the third conclusion, this is N, right? The third thing we can prove is that the interior angles on the same side are equal to the sum is going to be equal to 180 degrees. So this means angle 2 plus angle 4 is going to be 180. Okay, so just the fact or just the assumption of two parallel lines, then you can prove these three conclusions. Okay, so this is essentially one of the proposition we are going to prove. Okay, third statement, this is proposition 1.30, and this is kind of intuitive. It says straight lines parallel to the same straight lines are also parallel to one another. In more modern notation, it says if you have line L parallel to K, but at the same time, K also parallel to M. So essentially M and L are parallel to the same line, okay? Then the conclusion you can get is that then L has to be parallel to M, right? I mean, from the picture, you can see very clearly, right? If L is parallel to and M is parallel to the same line, then each of them should be parallel to each other, okay? So this is quite intuitive. And this is 1.30, one of another proposition. And the last two, first one is called Proclus axiom. Proclus is one of the philosophers back in the Greek ancient time. It says if a line cuts through one of the two parallel lines, right? So if you have maybe say line 1 and line 2, if one of them cut, let's say M, cut L1, right? Then M has to cut L2 as well, which is also pretty intuitive, right? You have two parallel lines. If you just drove some other line crossing one of them, they has to cross another one because those two are parallel, okay? So it's not too bad. The statements are not too hard to imagine because, I mean, we can draw the picture and see that's true. The last one is huge, is actually, let me put a highlight here because we definitely saw, I think I introduced this earlier before. This is the favorite alternative or substitute for fifth postulate that everyone loves. And a lot of people, when they talk about parallel postulate, they actually refer to Playfair's axiom instead of fifth postulate because this one is more commonly used in some sense. So it says, if you have a point, through a point, not on a given line, right? That's called this point P. There exists at most one straight line through this point P, which is parallel to this given line L, okay? As you can see that in Euclidean geometry, in the plane that in the world that we live with, this has to be true, right? There cannot be more than one parallel line that's passing through this point P, okay? So now you might wonder, how are we going to prove that these 5 are equivalent, right? If you want to if you think about it, does that mean that I'm going to prove so many, like 1 equals 2, 2 equals 1, something like that? It turns out that for this type of theorem, right, like this is actually very useful, especially, let's say, if you're a math major or even math minor, let's say if you're going to take more advanced math course, this kind of theorem is very spatial because we are proving 5 statements are equivalent, right? Equivalent means one imply the other, right? Doesn't matter which one implies which. So in some sense, you need to show me 1 implies 3, 3 implies 5, or 5 implies 1, doesn't matter, right? But there's a economical way to prove it, right? So the economical way is the following. So let me write down. To prove they're all equivalent, essentially we create a loop, a chain, and that's all we need. So the strategy here is we're going to prove statement 1 implies 2, and we prove 2 implies 3, 3 implies 4, 4 implies 1, and then we need to like close the loop. We can close the chain. Essentially, eventually we need to prove 5 implies 1. After we do this, how many? 1, 2, 3, 4, 5. So essentially, you need to prove 5 things, right? After we prove or close up this chain, then we can claim that any one of this statement will follow from another. So you might argue, say, then how are we going to say 2 imply 1, right? If you start from 2, right, you want to say imply 1, even though we didn't directly prove it, but because you already proved this chain, right? Starting from 2, if you want to prove 1 holds, and then you can go through the chain, right? You can get 2 from 3, 3 from 2, right? 2 implies 3, 3 implies 4, 4 implies 1, and 5 implies 1, right? So you can say that even you start from 2, eventually you will reach 1. So it really doesn't matter which statement you start from. After you finish up this chain of proof, you essentially prove that any one of them implied any one of other. Okay, so that's essentially the strategy. This might be the first time you solve such kind of proof. So I'm going to see that how far I can go. So first, I can tell you that if you already read the textbook, then I really appreciate. If not, that's okay. I can tell you the proof. I said there are 5 of them, right? Except the first and the last one, the middle one, right? Let me circle out. 2 implies 3, 3 implies 4, and 4 implies 5 should be the most easier one. There are only like three lines, I would say, 3, 4 lines. So if you want to start with the easier one, then you know like these 3 in the middle will be the easiest one. The first and the last one takes a little bit more time. First one is not too bad. The most difficult or longest one is the last one, okay? So let's see. So when you prove this, you need to keep in mind that do not use something you haven't justified, right? So for the first part, you want to prove that the statement 1 implies statement 2. Statement 1 is essentially the 5th postulate, and I copy here, right? Just copy here in case we need to refer, okay? So how are we going to do this? Essentially, we say, okay, we assume 5th postulate, that's the statement 1. We want to prove statement 2. What's statement 2? Statement 2 is essentially what I'm writing down here. So assuming 5th postulate, essentially I have 2 parallel straight lines, A, B, and C, D. And we have the transversal EF. And essentially, the second statement claim that the angle 1 should be equal to angle 2, and angle 1 equals angle 3. And also angle 1 plus angle 4, it's going to be 180. This A, B, and C are the things that we want to prove, assuming 5th postulate is true. Okay, so whenever you encounter this kind of proof, you need to remind yourself that because I assume the whole point is to use 5th postulate, the statement 1, to prove this A, B, and C. So at some point, you should realize that you're going to use or need 5th postulate. If you didn't use it, then it might mean something is wrong, right? Because essentially the whole goal is to use statement 1 to prove statement 2. But if it turns out that in the proof you don't see statement 1 at all, then maybe something is wrong. Okay, so that's an indication that how to do such a proof. And as I said, most of the proof here you're going to see is by contradiction. Okay, so the contradiction part is only for the part A. Once you have A, B, and C is kind of straightforward byproduct. Okay, so for part A, we do proof by contradiction. Okay, so part A, we want to prove if you have 2 parallel lines, then angle 2 and 1 are equal. Okay, so again, I want to emphasize, this is on the assumption that fifth postulate is true, okay? But we assume the contradiction, we assume otherwise. What if angle 1 is not equal to angle 2? Then, I mean, if it's not equal, then one of them has to be larger. So then we say, just without loss of generality, we say, okay, assuming then in this case, let's say what happened if angle 2 is bigger than angle 1, right? Then we're going to see what happened. Then if angle 2 is bigger than angle 1, then if we add both angle 4 on both sides, then we're going to have that angle 2 plus angle 4 is going to be bigger than angle 1 plus angle 4. You add the same angle on the same side, so the relationship still hold, right? So then by proposition 1.13, essentially we know that those angle 2 plus angle 4 are equal to 180, right? So let me remind you, because proposition 1.13 is essentially tells you that if you have supplementary angles, right, that essentially adjacent angle next to each other along a line, then they're going to add up to 180. So let me put so because they are supplementary angles, right? So what does this mean? Then it means, let's put all the information together. So we have angle 2 plus angle 4 is 180, right? So that's 180 here, right? So that means you're telling me angle 1 plus angle 4 is going to be less than 180, right? Because the 2 plus 4 is going to be 180, okay? So now you can see what's 1 and 4, right? So if you look at the picture here, 1 and 4 is exactly the interior angle on the same side, right? So you can see now is exactly the moment we are going to use fifth postulate, right? So if you want to be more comfortable about the thing, let me just prove like instead of 1 and 2, let's put 4 here so you can see exactly what we have here, right? So we just said that 1 and 4 is going to be, the sum of 1 and 4 is going to be less than 180. And that's essentially where we can use fifth postulate. And if that's the case, then fifth postulate is going to tell us that L and M, that those two lines are intersecting, right? So now we come back, right? So if 1 and 4 are less than 180, then by fifth postulate, it implies these two lines should intersect, right? Will intersect, will meet each other, right? But essentially you will see that, oh, this is not true, right? Because I just start from assuming these two lines are parallel, right? So this is essentially contradict to our very assumption. Will contradict to the assumption that this two line was originally assumed to be parallel, right? So that means what we start with is wrong. That means angle 1 cannot be not equal to 2, which means it has to be equal. Okay, so actually I write out a lot of like detail and like something, but you can see that the argument is not too bad. You just need one extra step, right? Once you get to the point where the interior angle on the same side is the sum is less than 180, then because we assume fifth postulate is true, so we use fifth postulate to, no, because we didn't prove 1 plus 4 is 180, right? Actually, this is something we want to prove, but not prove yet. This is exactly what I meant, that you should be careful, don't get into the loop, right? We want to prove A, and C is not proving yet. So you cannot use the conclusion from C, right? Be careful the logic here. We are going to use the conclusion of A, which we just proved, to prove part C, right? So you cannot use the fact. So it's not contradict to what you just said. Yeah, so be careful. Okay, so you should not use C. This is exactly the common mistake I saw last year, that people confuse which one is already proved, which one is not. Okay, so here, only thing you can use is everything before here, right? Everything before here, including the fifth postulate. That's it. Okay, so for, as I said, once you've done A, B and C is the byproduct of A. Okay, so for B, so what's B? B, we want to prove angle 3 is equal to angle 1. And keep in mind, we already proved A. So we know angle 1 is supposed to be equal to angle 2. Okay, so now that's C. So since we already know, okay, so in order to prove 1 equals 3, we are going to use the advantage of 2 and 3 here. So maybe let me put another picture here so you can compare, because the picture is, I'm going to roll down. Okay, let me copy down the picture. Okay, so now since angle 2 equals angle 3 by proposition 15, which is essentially the vertical angle theorem, right? Because they are vertical angle to each other, 2 and 3, right? So, and we just prove in A that 1 equals 2, right? So if you put this together, then we right away obtain 1 equals 3, right? That's it. Okay, so I can say B is really just one line proof from A, okay? So you need to be careful, right? When you prove A, you should not use or assume B and C. That's haven't been proved yet, okay? And same thing for C. C is also a byproduct of A, and so you can see now, or B essentially. So now we know 1 equals 3 from B, right? Then we obtain that 1 plus 4 is going to be the same as 3 plus 4, right? Because 1 equals 3, okay? And by proposition 1.13, which is the supplementary angle, we know again, because 3 and 4 are supplementary for each other. So 3 and 4 is 180, right? So this is already known by the existing proposition. So we obtain that essentially, I mean, if right-hand side is 180, left-hand side is also 180. And this is exactly what we want to prove, right? 1 plus 4 is 180, okay? So you can see that once we prove A, we can use A to prove B. Once we prove B, we can use B to prove C. You might argue with me that if you think about it, the logic, you might argue with me that can I do the other way around, right? It's possibly that you could. I haven't really think through here. You might start from B and trying to prove A and C, right? That's okay, as long as that when you trying to do the proof, you don't use something that's not proven, right? So here I believe this is the easiest way to do it. You start from A and prove B and C, right? You might be able to start from B and prove A and C. If you do so, when you prove prove B, then you should not use the other two statements, right? So just be careful that I've seen this kind of loop logic a lot, that people forgot that what's already proved and what's not proven, and then accidentally use something that's not proven. This is exactly the common issue that I saw in the previous couple homeworks, that some people directly use like Pythagorean theorem that we haven't proved, or use some other things. Okay, so that's thing you want to be careful. Okay, so I think we have time, maybe do another one or two. So let's see. So now we want to prove, so we have proof just now, 1 implies 2. Now we want to prove statement 2 implies 3. So statement 2 is, again, I copied down here, that it's just actually exactly what we just proved. Euclid's proposition 29. So essentially it tells you if you have two parallel lines, then the angle 1 equals 2 and 2 equals 3 here, and then 2 plus 4 equals 180. I changed the numbering here, sorry. But it's essentially pretty much the same thing, right? So I'm going to use this proposition 1.29 to prove the third statement. The third statement is 1.30, which essentially tells you if you have two lines parallel to the same line, then those two lines should be parallel, okay? So let's see the setup here. So it says, assuming now, because we are using second statement to prove the third one, so we are assuming the second statement, the proposition 1.29, okay? So you assume 1.29, and you have three lines here, A, B, C, D, and E, F. And you want to say that if AB is parallel to EF, at the same time, CD is also parallel to EF. And we want to prove that eventually AB is going to parallel to CD, right? Because they are parallel to the same line. That's exactly the statement of 1.30, okay? So again, you're going to see this is proof by contradiction, okay? So to save some time, I just already wrote down the statement here. So it's going to be a little bit fast because I'm just saying all these things. So I believe if this is the first time you saw this statement, you need to really think about it. It's not that easy because you need to kind of let the logic click there. So I would suggest you definitely go back to review the proof of this one. You're going to learn a lot from this particular theorem. And believe me, once you sit down and then be patient, read through the thing, it's not that bad, the proof, okay? So first of all, proof by contradiction, right? So eventually I want to prove that AB is parallel to CD. So with the assumption of the proposition 1.29, this statement here is true, I also assume AB is parallel to EF, CD is parallel to EF. And this time I use contradiction. So I'm going to assume, what if AB is not parallel to CD? And I want to see that how can we get the contradiction, okay? If AB is not parallel to CD, then it will intersect at some point, whatever that point is. So that's called the point that intersect, that's point G. This is the point I draw here, okay? So now this proof is a little bit special. We haven't seen such proof before. Now from here, so you see that this picture satisfies the assumption, right? AB is parallel to EF, okay? But even though the picture is a little bit misleading, we did assume that CD is parallel to EF, okay? But because we use proof by contradiction, so the picture looks odd, right? So now with this intersection, point G, we want to use proposition 1.12 to construct a perpendicular line from G to EF. This is doable by the construction theorem, construction proposition 1.12, okay? So now we can construct such a line from G to EF, and this is perpendicular. Okay, and that's called the intersection at EF, this point, let me call it H, okay? So now let's see, from this picture, since AB is parallel to EF, this is given, okay? Now this is where we use the proposition 1.29, right? So let's see, if you have two parallel lines, what happened? So we're going to have angle AGH is going to be equal to GHF. So GHF is this, and AGH is this one. So this is essentially the interior alternate angle, right? So let's go back to 1.29. This is exactly the part A, where interior alternate angle are equal if you have two parallel lines. So you can see, right, I'm using statement 2 to prove statement 3. So at some point, I'm going to use statement 2, right? So that's where we use it, right? So now we have these two red angle I put here are equal. And similarly, this is given, right? This is also from the given assumption that CD is going to parallel to EF. Okay, that's why I say the picture can be a bit misleading, because we are doing a proof by contradiction. So then, because CD is parallel to EF, so then we're going to use proposition 1.29 again to claim that the interior alternate angle CGH is going to be the same as this GHF, right? Of course, it's not the same, but you can see that that's where the contradicts come from. Okay, so we're going to have CGH equal to GHF. Then if you combine this, right, I mean, on the right-hand side, you both have GHF. So the left-hand side is going to be equal. So this tells me that the red angle AGH is going to be equal to CGH, which is definitely a contradiction from what you saw, right? This contradicts the common notion, right? Because essentially CGH is part of like AGH, right? From the picture, right? So this, I mean, CGH is supposed to be smaller, right? Okay, so that's essentially the contradiction, right? Then it contradicts to something we already know, meaning we cannot assume, we should not start from assuming AB is not parallel to CD, which means the conclusion we want, AB is parallel to CD. Okay, so proof by contradiction can be a little bit tricky in the sense that like you need to really carefully think about the logic here. And it takes time, definitely takes time. You need to be very concentrating. You cannot just like, I don't know, read the proof and then watch some Netflix or come back. I mean, this doesn't work. You need to really concentrate and read through the whole thing so you get the logic here. I think we have time to do one more because, as I said, this the middle three are actually easier. So now I want to prove 3 implies 4. And you can see that most of them are going to be proved by contradiction. So this one is not too bad. So what's statement 3? Statement 3 is the thing we just proved. Tells me that if you have 2 lines parallel to the same lines, then they're parallel to each other. We're going to use this third statement to prove the fourth one. What's the fourth one, right? Let me remind you, fourth one tells you if you have 2 parallel lines, let's say L parallel to M, and you have another third line that's called K, which intersect one of these 2 parallel lines. So let's say if K intersect M, you want to show that this K also intersect the other line, L, as well, right? So this is something we want to prove. And in order to prove the statement 4, we want to assume that this proposition 1.30 is true, okay? Which means at some point in my proof, I'm going to use proposition 1.30, okay? So this is actually not too bad. You need to kind of think about the logic here. You can see that it's quite straightforward. The proof is quite short. So let's assume that, I mean, so proof by contradiction, right? We already assume L is parallel to M and K intersect M. And the goal is to prove that K intersect L as well. So to assume the contrary, I assume that K does not intersect L at all. Okay, right? So I want to prove K intersect L, but I want to use proof by contradiction. So I assume what if K does not intersect L? Then that means what if K is parallel to L? And I want to reach to a contradiction at some point, okay? Then, okay, so first assume this, right? Okay, we have this assumption here, but we also have L parallel to M, right? This is given. Then now you can see that both K and M are parallel to the common line L. And that's exactly the statement we want to use for proposition 1.30, right? So let's go back. 1.30 says if you have 2 lines, L and M, parallel to the same line, K, then the other 2 are parallel. So now we have K parallel to L, L parallel to M. Then by the proposition 1.30, the statement 3, we know that M should parallel to K, right? That's essentially by what we assume, which is the proposition 1.30. But then we already got the contradiction, right? So you can say that this will essentially contradict to our assumption, right? Remember, you can see that our very assumption here is that we start with K intersecting M. But after you assume the contrary and you do all the like logical steps, at some point you reach M parallel to K, right? That's essentially contradict to what we just start with, okay? So it means then essentially what we start with is wrong, meaning K should intersect L, okay? So this is essentially how they prove. And then you can see if you use 3 implies 4, it's quite straightforward. It's just, I don't know, 3 lines of proof by contradiction. But again, it doesn't mean it's easy. You need to really think about the logic here. So because the time being, I think I might have, let me see, do I have another time? Yeah, I probably can do this one as well. But after I do the middle 3, I'm going to stop because then it will be, the last one will be too hard, okay? So the 4 to 5 is, what's number 4? Essentially 4 is what we just saw, the pro-clause axiom. If one line cuts one of the 2 parallel lines, it should cut the other one, right? This is what we just proved. We're going to use this to imply the statement 5. The statement 5 is essentially the famous Playfair axiom. So we assume pro-clause axiom, right? Assume statement 4. We want to prove if you given a line L and the points outside L, we want to prove that there exists at most one parallel line that's passing through the point P and parallel to L. This is Playfair statement, right? So we want to use pro-clause axiom to prove the Playfair axiom here, okay? So we given a line L and a point P outside the line. We want to prove that there exists at most one line that's parallel to L, but at the same time passing through P, okay? You can have at most one, okay? So how to do the contradiction, right? So contradiction sometimes is hard is because you need to find the contradict of it, right? So what's the negative of at most one, right? Then the negative of at most one means that it's more than one, right? So instead of at most one, I want to assume what if there are more than one such parallel line exist, right? More than one, of course, you can say 2 or 3 or 4, but we can just use 2 is enough, okay? So we say, okay, now we have 2 lines, L and M, passing through the same point P, and both K and M are going to parallel to this line L, okay? So you're going to have, let me draw this picture. So now you're going to have P and this L, right? So instead of just only one line being parallel, I actually have 2. Okay, my picture might be a little bit misleading, but let's just say, okay, you have now 2 parallel lines. Of course, it's not correct, right? So that's why we need to prove it. So let's say we have more than one parallel line passing through P, and let's say a K and M, okay? But you can see that K and M, because they pass through the same point P, so that means they intersect at least at point P, right? They already passed through the same point, they have to intersect at P, right? Then if you can see that K intersect M at P, then that's where we can use the pro-clause axiom, right? Pro-clause says, go back, if one line cuts one of the 2 parallel lines, then it cuts the other, right? So by pro-clause axiom, since we already know M parallel to L, and essentially K meet M, right, at P, then it means K should also intersect L. That's by pro-clause, okay? Yeah, so sorry, I'm being a little bit over time, just want to finish this. So then in this case, then, I mean, we got the conclusion because by pro-clause, we know in this case, K should also intersect the other parallel line L. But we just start with K parallel to L, right? So you essentially right away see a contradicting statement here, right? On one side, we say K intersect L. On the other side, we start with K parallel to L, so they contradict, right? So this means that it should exist at most one parallel line passing through P. Okay, so that's it. Sorry for the over time. I want to be able to finish up the 3 easy one. But I definitely strongly recommend that you go back to watch the video or maybe read the textbook. These 3 middle proofs should not be too bad. You just need to have time to kind of read it through. So if time permit, I will come back with the last one. The last one is the longest one. And do me a favor, please start reading 7.1 and also keep reading. On Wednesday, we definitely at least will be able to cover 7.2 and 0.3 because that's actually much shorter section. Okay, so if you have any question, please stay. Otherwise, you're free to go. Sorry for like overtime.
Thank you.
Thank you. Hello, hi. Okay, so did you hear what I said at the beginning about some hints for the problem 2, I guess? Yeah.
I remember slightly, yeah.
Okay, so yeah, so you told me that you have some question about the number 2. So so what exactly the question is, because there are actually several parts of them.
My question was, I just wasn't able to figure out how I would draw the photos. It said the hint was to do it with lines and dots instead of pizzas, but
so do you understand the question 1? Because the question 1 essentially used the example from the section 6.2, right? If you understand the logic, then the same logic applies here, right? So yeah. Okay, so for example, let's say so okay, part B, are you able to construct a picture that represent this geometry, meaning a picture that's all the 4 axioms are satisfied? Are you be able to
does it need to be one singular photo or
one
picture?
Singular? Everything is one singular because it says
okay.
construct a diagram, right, to represent the geometry, meaning part B, for example, you need to construct a picture where, of course, you want to construct just one, right? Satisfy the whole thing. That's called a model, right? Yeah. So yeah, so essentially you want to, for part B in particular, you want to construct a picture that essentially all the 4 axioms you saw here satisfy in one picture.
Okay.
Yeah. So have you read the 6.2 yet?
Yes.
Okay. And for part C, so like, for example, for the part B, right, you need to first make sure it's exactly 3 points, right? I mean, that's kind of easy to satisfy. And axiom 2, 3, and 4, it tells you that first axiom 2, it says you need to make sure between 2 different points, there's only one line, exactly one line passing through these 2 points. Right? Okay. Yeah. So actually the picture you're going to see is, I can only think of maybe one in particular, like that satisfied this. And don't overthink, as long as it satisfies all the 4 axioms, then that will be the picture. But you need to really show me, like check mark that it really satisfies all of the axioms.
Oh, okay.
Yeah.
So wouldn't it just be a triangle?
Yeah, exactly. Okay. Yeah, because that actually satisfies. Or actually, technically, let me share the thing that, I mean, you can say it's a triangle, or actually because the line here is not really the usual line as what I just said. So, I mean, some people might draw me this, that's okay, as long as they indicate the 3 points they have is here, right? You can have L1, L2, L3, right? Because the line here is not what we thought. You can think of the line here as some kind of committee, right? So you can say that, oh, L3 committee contains person A and person B, right? And L1 committee contains person B and C. L2 contains A and C. So that's why. So you can say each two persons should be in one common committee, something like that. So even like it seems like that you have some other points elsewhere. It's not, so for example, you don't really have point here, right? I mean, it's not the usual sense of line we think of. That's what you need to be careful. Yeah. And how to do C, D, E, F, they're the same logic. So to say, take C, for example, you want to use one model, A model, to show that axon 1 is independent. So the idea to do so, if you already know the logic of the textbook example, essentially what you need to do is to come up with a picture where axon 1 is wrong, but axon 2 and 3 and 4 are all correct. So why this will tells me that axon 1 is independent of 2, 3, and 4? Because if it's not, right, so you need to know what independent means. Independent or dependent means one relies on 2 and 3 and 4. In other words, one can be derived from 2, 3, and 4, right? If it's not independent, then, so let's say you have some picture, whatever this picture is, right? And you know 2, 3, and 4 already hold, right? If one really relies on 2 and 3 and 4, then it should be able to be proved from 2, 3, and 4, right? So if you have a picture where 2, 3, and 4 that is valid here, then automatically one should also be hold if one really relies on the other 3, right? But you successfully find, you essentially now, if you can draw me a picture where 2, 3, 4 hold, but not 1, then essentially it tells me that 1 cannot be proved from 2, 3, and 4, right? That's essentially the logic here. So how do you find this picture, right? So you want a picture where axon 1 is violated. So axon 1 says there exist exactly 3 points. So this is exactly what I said at the beginning of the class, that for this particular part C, you may want to find more than 3 points. The textbook example somehow use lesser point, but I think this particular part C, you probably need more than 3 points, right? As long as it's more than 3 points, that violates axon 1, right? So you want to draw a picture that has more than 3 points, but at the same time, axon 2, 3, and 4 are satisfied. Okay, you need to kind of think about it, right? So my hint for you is that you can draw maybe a line here with 3 points here, right?
Yeah.
And then another one here. And you need to maybe connect some of them to make sure all the axioms are hold, right? But so now you will have 4 points. Okay, that's the hint I can give to you. Yeah. So so in order to violate 1, I would say the better way for this part is to have more than 3 points. But you need to make sure that the other 3 axioms, the axiom 2, 3, and 4, are satisfied. So that's for part C. And same logic holds for D, E, and F. So in order to prove axiom 2 is independent, that means you want to draw a model. This is part C, right? Part D is you want to draw whatever a picture where axiom 1, 3, 4 are all hold, but axiom 2 violated, right? So axiom 2 means any 2 distinct points are on exactly 1 line. So you might want to draw a picture, and because you need to satisfy axiom 1, so you need to draw exactly 3 points. But you need to see how you create this corresponding picture where there might be 2 different points, and there's either no line passing it or maybe more than 1 line passing it, right? So you want to try to draw a picture violating axiom 2 while the other 3 are okay. Does that make sense?
Yes.
Okay, so this is like a puzzle. I don't think this is that hard, So my suggestion is try this again and see whether you can draw the picture. And as I said, the textbook example, or you can say the exercise 1 would be a good reference. If you can understand the logic there, or you might be able to use some of the tips from there, like the example they mentioned in the 4-point geometry they mentioned in this section. That would be a very good example to refer to as well. Yeah.
Okay.
Yeah. So I want to stop here. I want you to try a little bit and see whether you can work this out. And think about this. If you can, let me know, like for example, tomorrow, then we can talk about it. Like I can email you further hint or something. Or if you're not sure, ask, like draw some picture and it's like take a picture and send it to me. Then I can kind of check it for you and see maybe it missed something or is it correct, something like that. Yeah.
Okay.
Okay, so let me stop share here. Actually, I don't know why the other 2 people are still here, but they probably are listening. That's fine. So let me stop recording because that's